Hello and welcome back. Polar coordinates enrichment for today. 5-star question. This is 2 questions I wrote only the other day. I've already done a video on the first of those two, which was not too bad. And this is now the harder version, not harder versions, nothing to do with one another really. The harder of the 2 questions that I made, but I have no idea in what order I will upload the 2 questions. So you might see this one that I'm going to do now first, or the other way around. I have no idea. Okay, let's see what this question is actually saying. A cardioid has polar equation. Let's write it is R is 4 1 plus the cos of theta, and it's defined between 0 and pi over 2, so it's not the whole cardioid there. I'm writing stupid things there. 0 to pi over 2. It doesn't really matter whether it's inclusive or not. I'm sure it doesn't. It's inclusive actually on this particular question, but it hardly matters. Okay, what does he actually ask us to do? A tangent to the curve at some point P has gradient -1. Find in the form R is a function of theta the polar equation of this tangent. So just try to get a picture and just see what's going on. The cardioid is only going to be on the first quadrant of a Cartesian set of coordinates. So something like this. And there's a point P here. And the tangent at P has gradient -1. So grad -1. Okay, so we need to find the equation of this tangent in polar coordinates. We have, of course, the equation of the polar curve. Okay, so what is the starting point for something like this? Well, quite clearly, the starting point is the gradient. We've got nothing else but gradient, really, to start. The gradient we know is -1. So dy by dx, quite clearly, is equal to -1, but I'm not going to write equal to -1 because I have no expression for this gradient yet. And I want an expression in polars given my question is in polar. So what do I do? All right, I'm going to write divide top and bottom by d theta. So dy by d theta over dx by d theta. And of course, that means d by d theta of your y and d by d theta of your x, but there's no closing the brackets because I'm going to replace them in a minute if you're just wondering. So what is my y? My y in polar coordinates is, of course, r sine theta, and my x is r cos theta. All right, so this is now, I need to carry out these differentiations. So d by d theta, r is 4 bracket 1 plus cos theta, multiplying a sine theta. And at the bottom, I have I wrote d by dx there, sorry. D by d theta is meant to be there. D by d theta of 4, 1 plus cos theta, that's my r, but this time it gets multiplied by the cos of theta. Okay, careful, this is not a quotient rule. It's separate differentiations on top and bottom. This 4 is a constant, multiplicative constant. I can move it to the front of either of these differentials and cancel it. So this I can throw away. Shall I multiply the brackets before I differentiate, or shall I leave it like that? Let's leave it like that and see what happens. It's not that hard anyway, the differentiation. So looking at the top, first of all, differentiate the bracket minus sine theta times another sine theta, let's make it squared, plus leave the bracket alone, 1 plus the cos of theta. Differentiate your sine, it's going to go to a plus cos. And at the bottom, differentiate this bracket, a minus sine of theta times the cos of theta, untouched, and then leave the bracket alone, 1 plus the cos of theta, and differentiate the cos into, it's going to go to a minus sine. So I'm going to write the sine here and put a minus at the front there. A bit of a tidy, so we're going to get a minus sine squared, I'm writing x there stupidly, sine squared theta plus a cos of theta plus a cos squared of theta. And at the bottom, I'm going to get minus sine theta cos theta minus a sine theta minus another sine theta cos theta. So I've got 2 of this now, sine theta cos theta. And the final tidy for this, cos squared minus sine squared is definitely the cos of 2 theta, the standard A-level identities, plus a cos of theta. And at the bottom, I'm going to get a minus sine theta from here. And I got 2 lots of this, 2 negative lots of this, but this will be now a sine of 2 theta identity. That's 2 sine theta cos theta. Okay, and of course that is equal to minus 1. So let's set it equal to minus 1 now. I'm being a bit sloppy with how I'm writing things. And in the time it takes me to rub off this board, let's think how we're going to solve the resulting equation. The equation, of course, the next step is kind of obvious. Times it across. It will get rid of the minuses. That's good. But I don't like the look of the rest in there. Okay, so let's think. So let's write it up here again. Cos of 2 theta plus the cos of theta is equal to the sine of theta plus the sine of 2 theta. Okay, what next? This is a problematic equation because I've got 2 thetas in 2 places, and the problem is it doesn't matter how I break it. I do not think at the moment this can be written in terms of causes and sines only. It's going to be a mess. I can think of one way, and I'm trying to avoid it. And I'm trying to avoid it because I don't remember the identities that I need. But it looks like I'm going to have to go that way. It's not difficult. It's just that I don't know the identities by heart. Okay. This identities are in the formula booklet. So if you're doing standard, even if you're doing advanced papers, I think they still give you this identities. However, this question for me is going to go to one of my SPX papers. In SPX special extension, no formulas are allowed of any sort or any calculating aids, and therefore either you know the identities by heart. Sorry about that. I don't remember them at this moment in time. Or you derive them. So this is going to make the video a little bit longer. I do apologize. So I'm going to have to come out. It's actually good education to actually see how to derive identities when you need them, and it's not that long. Okay, so I'm going to get the addition of causes. So I'm going to do cos A plus B cos A minus B. It will only take a few minutes, maybe 3 minutes or something. I'm going to rush through here, so I do apologize if I'm going a little bit fast. Cos, sine, sine. So cos A, cos B minus sine A, sine B. And exactly the same. Cos A, cos B plus sine A, sine B. And because I want to add the 2 causes, I need to have cos A plus B plus the cos of A minus B. When I add them, this will cancel, and I got 2 lots of that. So it's going to be 2 cos A, cos B. And if I let this be P, and this Q, this will be P plus Q over 2, and this will be P minus Q over 2. So I derived the first identity already. So that is the cos of P plus the cos of Q is equal to 2 lots of the cos of P plus Q over 2 times the cos of P minus Q over 2. So the first one is done. Wasn't that bad. So we're going to have to do the same thing for sines now, for the right hand side of this equation. So let's change that into sines. So we got the sine of A plus B, and the same one for the other one. That goes sine A cos B plus cos A sine B, and exactly the same but for the minus. All right, we need them to add. So again, it's going to be sine A plus B plus the sine of A minus B. Maybe, of course, this will cancel on addition, so I've got 2 lots of that. 2 sine A cos B. And again, I'm going to put P, Q, and it's exactly the same transformation equations. So the sine of P plus the sine of Q, sine P plus sine Q, is equal to 2 lots of the sine of P plus Q over 2 cos of p minus q over 2. So I derive my identities. And as I said, it wasn't that long. It's actually faster. It's just I'm getting lazy in my old age and I don't want to write stuff down. Okay, so now this equation can be simplified. So I'm using this identity on the left. So that's 2 lots. Cos, add and divide by 2, 3 theta over 2. So 3 over 2 theta. And then the p minus q is 2 theta minus theta, which is just theta over 2. So cos theta over 2 is the same as 2. Looking at this identity, 2 there. Sine of 3 over 2 theta, adding and dividing by 2, times the cos now of theta minus 2 theta, which is minus theta. This I hope it doesn't bother you. I'm writing it straight away. It's enrichment anyway. You should understand what I'm doing in there. Whether if we subtract theta minus 2 theta or 2 theta minus theta, cos is an even function, so the minus that you're going to get in the argument, you can throw it away. Okay, this is the equation. Get rid of these 2's. Cos theta over 2, does it give me any solutions, or can I divide it out? What's going on? Cos theta over 2 is equal to 0, so I can see if I can throw it away. Of course, it'll give me theta over 2 is equal to, I'm sorry I'm going into degrees because I'm thinking in degrees much quicker, plus or minus 90 plus or minus 360 n, and therefore my theta will be 180 plus or minus, of course, with repeats of 720. The range for this is 0 to 90, not to pi over 2. There's nothing in there from this particular bit, and therefore I can safely divide it out. I can throw it away. Normally, I will be moving things to one side and factorize the cos theta over 2 out, but here I don't have to. So goodbye, my friend, because there's no solutions. Okay, so all I'm left with is a very simple equation. Sine of 3 over 2 theta, divide to make a tan of 3 over 2 theta is equal to 1, and therefore this will produce very simple equations. So sorry, solutions, I beg your pardon. 3 over 2 theta, the arctan of 1 is pi over 4 with repeats of pi, so times by 2, divide by 3, 90, 60, sorry, it's 30, so it's pi over 6 with repeats of 2/3 n pi. Only solution is in fact pi over 6. So we have found the polar coordinates, or not quite, but the theta value is pi over 6 here. Okay, so if you look at the point P, we know that this is pi over 6, and the value of r we're going to get from the equation of the curve. R is equal to 4. 1 plus cos of pi over 6 is root 3 over 2. Times it out, give us 4 plus 2 root 3. I don't know if I can fit in there. I'm going to write it slanted. 4 plus 2 or root 3. These are the polar coordinates of the point P. So let's clear the board and let's think what's our next move. What are we trying to find? We're trying to find the polar equation of this particular tangent. Okay. There are ways we can find equations of lines given polar coordinates. Some of them are very easy, but some of them are not so straightforward. For me, there's no way I'm going to tax my brain now at this moment to think polar. I'm going to work a Cartesian equation of this line and then switch into polar. I think that's the sensible thing to do. But for this, of course, remember these are polar coordinates. I need Cartesian coordinates. And that's not difficult, just a quick geometric picture to give us these values. So here's a triangle. That's this triangle here, basically, I'm drawing. The r, which is the hypotenuse, is 4 plus 2 root 3. That's going to be my x, and it's going to be my y, and this is, of course, pi over 6, or 30 degrees. So my y is that 4 plus 2 root 3 times the sine of pi over 6, which is a half, and this will give me 2 plus root 3. That's the y coordinate. The x coordinate is that 4 plus 2 root 3 times the cos of pi over 6, which of course is root 3 over 2. This will simplify to 2 root 3, and the 2 will cancel here. Root 3 times root 3 is 3. So these are now my Cartesian coordinates. I think I can just squeeze the equation of the tangent there. Y minus the y coordinate of my point. Y minus 2 minus root 3 is equal to the gradient, which is minus 1, bracket, x minus the x coordinate of my point, which is minus 2 root 3 minus 3. Okay, let's multiply this out. Y minus 2 minus root 3 is equal to minus x plus 2 root 3 plus 3. And from there, probably better to put the x and the y's together on one side and sort these numbers on the right hand side of this expression. So I got a 5 from the whole bits there, and I've got a plus 3 root 3. So that's the Cartesian equation. All is left for me now is to switch that into polar coordinates. Is that difficult to do? The answer is no, because if you look at what x and y are in polar, this is r sine theta plus r cos theta is equal to this mess, 5 plus 3 root 3, which means we can factorize the r, sine theta plus cos theta in a bracket is equal to 5 plus 3 root 3. And therefore, let's use a different color pen. Let's do it in, let's say, in purple. I found, because it does say, find in the form r is a function of theta, the polar equation of this tangent, and that is going to be r is equal to a not so nice number, 5 plus 3 root 3, we cannot have it all, sine theta plus cos theta. Okay, I think that's pretty much done. I don't know what you thought of this question. I thought it was actually quite tough, and I do apologize. I did go a little bit fast. It's because I was conscious my videos are a little bit long, and I lost time when I had to derive these identities in there. So I sped up, but I hope on YouTube, of course, you can always pause it and just fill in the missing gaps, if indeed I left any missing gaps. For the time being, that is all, and I will be signing out.